Welcome back to our series on electricity and magnetism. In this episode, we're going to talk about RC circuits. That is, a circuit that contains at least one resistor and one capacitor. We're going to begin with the simplest of RC circuits, that is a single loop circuit with one resistor and one capacitor. What makes capacitor circuits different from resistor circuits is that they don't immediately reach their steady state. They have to pass through what's called a transient state. If a circuit only contains resistors, basically as soon as the battery is connected, all of the currents immediately jump to their final values, and they hold that equilibrium value all the while current is provided by the battery. But an RC circuit actually changes the voltage in each element as a result of the charging of the capacitor. As current flows into the capacitor, a voltage will arise here, and in essence, the capacitor is going to turn into a reverse battery. It's going to store charge and gain voltage until its voltage equals the voltage of the EMF that's driving it. When that happens, the current in the circuit will turn off, which means the resistor will only have a voltage drop across it while the capacitor is uncharged. As soon as the capacitor is fully charged, the current will stop and the voltage across the resistor will end. That means this current is not a constant current, but rather it changes as a function of time. And so we're going to have to encounter this circuit in two ways. The first way is called the transient phase, and that's what happens between the time the circuit is first connected and the circuit reaches full charge. When it reaches full charge, there's a new equilibrium or steady state, and of course there's an initial condition where we can predict all of the voltages. What we want to be interested in now, though, is what happens during that transient phase. Well, what we're going to fall back on is Kirchhoff's loop rule, because I have pretty well defined the voltage drops across all three of these elements while it's in operation. First, the battery. Again, I'm going to go through this loop in this direction, and of course there's only one loop, so I don't really need to label it. As I go around the loop, I'll have the EMF of the battery. I'll subtract the IR of the resistor because, of course, the current flows through it in the direction I'm going, so that's minus IR. And then finally, as the current flows into the capacitor, it deposits charge, and that charge is basically going to increase the voltage. So the voltage on the capacitor is a function of how much charge it has on it. It will also be negative because it'll charge positively at the top and negatively at the bottom. So in the direction I'm moving, that's plus to minus. So it represents a negative voltage. So that would be Q, the amount of charge on it, divided by its own capacitance. And that's just the formula for voltage taken from the definition of capacitance. And all this adds up to 0. Well, there's a problem with this equation, and that is it's not instantly solvable through algebraic means. And the reason for that is the definition of current is the time derivative of charge. This is a differential equation. If we rewrite it as such, it's I minus dq dt R minus Q over C, and that equals 0. So you can see we have the function Q, which is a function of time, the time it takes in order to deposit charge on the top plate, and it's also a function of the derivative of Q, the time derivative of it, the rate at which Q is changing. And any function that is the function of both a function of time and a time derivative of that function is known as a differential equation. Generally, solving differential equations is beyond the scope of this course. However, this is a separable differential equation, which we can solve by integration. As a result of that, this becomes very solvable for us. I'm just going to do some algebraic rearrangement here, and I'm just going to rewrite this equation in this form. The left side is dq divided by q minus EC, and the right side is going to be negative dt over RC. Go ahead and pause the video, and then you can algebraically manipulate this until it turns into this. They are the same function. It's just this one's been rearranged. And you can see why I rearranged it this way. Now it's in the form that's easy to take integrals of. If I wanted to integrate the left side, this is just a natural log of the function in the denominator. And if I want to integrate the right-hand side, it's just dt over a constant. So these are easy to integrate, and that's why this is a solvable differential equation. Let's apply the integrals to both sides and also include the limits of integration. I'm going to integrate this side from 0 to Q, Q being the function I'm looking for, how rapidly does the capacitor charge. And then the right side, I'm going to integrate that from 0 to t, t being that time later at which we are at charge Q. Okay, integrating each side is not very difficult. This side is the natural log of Q minus EC in between the limits 0 and q. And the right-hand side, I'll just go ahead and integrate and plug in the limits. It's negative t over RC, because of course the lower limit on the right-hand side was 0. Over here, the lower limit won't be 0 because the natural log is going to leave behind a residual function. So this will be the natural log of 1 minus q over EC once I plug in those limits. And the right-hand side is still negative t over RC. You can see what we'll do now, if q is my target to solve for, is I'll just raise each side as an exponential of the natural base. And that makes the left side 1 minus q over EC. And it makes the right side e to the negative t over RC. And then finally, I'm going to rearrange things to solve for q. So my final function, q of t, which is the amount of charge on the top plate as a function of time, will equal to the quantity EC times 1 minus e to the negative t over RC. And then I'm going to dress this up in two ways. I just want to relabel two things. If we look back at the original circuit, at the very end, after this guy has had a long time to run, I might be curious about what's the voltage on the capacitor at the end. Well, current will flow until the voltages match, which means the voltage drop across the capacitor has to be the EMF of the battery at the end. Let's take a look at what happens when that's the case. Again, the voltage across the capacitor is the charge divided by the capacitance. And in this case, that's equal to the EMF of the battery. And that means the quantity EC is actually equal to the charge at that time. And remember, we were talking about what happened after a long time when the capacitor was completely full. This represents the max charge. This is the most charge we can possibly fit on it. And notice that's the coefficient right there. So I'm just going to write that in, that this is Q max. The second thing I want to rewrite is this denominator right here. I'm going to replace that with the Greek letter tau. Tau represents RC. We have a special name for it. We call it the timing constant. And what it does is it's a quantity that represents whether or not this circuit reaches that equilibrium position where it stops charging rapidly or slowly. Notice the larger the resistance is, the longer this will take to fill because it will slow down the current. Also, the larger the capacitance is, the more charge can fit in it, so the larger it will take to fill. Tau is the timing constant, and it's a really nice indication of whether this is a fast RC or a slow RC. And so we'll replace RC with that tau. That means our final form for this equation is Q as a function of t equals Q max. And then that quantity is times 1 minus e to the negative t over tau. Now you might well ask, well, what value is that function? How often in a circuit are we interested in the amount of charge? And you're right, we generally aren't. The amount of charge isn't something we're generally interested in when we analyze circuits. What are we interested in? Well, we're really interested in current. What's the rate of current flow? And if this changes as a function of time, well then what is that? Well, here's the beauty of it. If this is the function for charge, then current is its derivative. I of t would just be dq of t dt. And this is a pretty easy function to take the derivative of, right? Once I know what the current is, I can then take this and run it through the resistor. So if I wanted the voltage drop across the resistor, well, that's just equal to R times I of t. If I want to know the exact voltage on the capacitor at any time, VR, or excuse me, VC, the voltage across the capacitor, that should be pretty easy because the voltage across a capacitor is just the charge divided by the capacitance. So that would be this Q of t divided by the capacitance. So you can see that once we have this function for Q, we have everything we want to analyze the circuit. Let's take a look at what this function looks like when it's graphed, and it'll give you a great chance to see how these RC circuits operate. So let's graph Q as a function of t. Well, this is often called a logical function. That is, it increases like it's exponential, but it only does so until it reaches a limit, and then it turns over and becomes an asymptote. The asymptote we already know. This is the max charge, which for this circuit is EC. The overall charge starts at 0, it climbs rapidly, and then it turns and approaches that line forever. And that's why we say after a long time, its value equals this. It will really take a very long time because the current slows at the rate at which the capacitor fills. And so it will slow to almost infinitely slow as soon as the capacitor's voltage reaches very, very close to the battery's voltage. Okay, that's what the transient portion of a capacitor circuit looks like. Now, this is the only one we can solve for because the mathematics of such a simple one-loop circuit was already complex enough. Once the RC circuits get more complex and add loops and additional capacitors, we will lose our ability to analyze the transient phase. But we can still analyze the steady state phase, and that's what we'll look at next. Here's a second RC circuit for us to look at, and unfortunately we will not be able to analyze the transient portion. The reason why is this resistor in parallel with the capacitor. There's no way to reduce this circuit down to a single loop. There'll be a different current in this branch, and this branch, and all of those currents will be changing during the charging phase because they're all functions of different amounts of charge change. That is, the current here and here may not be a function of the rate at which the capacitor is charging. Therefore, this will be beyond us mathematically. We'd end up with too many rates of change and not a separable, solvable differential equation for the mathematics we're capable of. But that doesn't mean we can't analyze it. Let's first take a look at it as if this circuit were uncharged. That is, the capacitor is empty and has no voltage to it, and the battery has just been hooked up. So we're going to consider at t equals 0. This is called a steady state analysis because we're not going to look at any time passing. We're just going to look at everything that's true right at the beginning. So the circuit has just been completed. I know that there is 0 voltage across the capacitor, and we know that because there's no charge on it. And that means Vc equals 0. Well, let's look at the implications of that. Once again, we've got a circuit that connects 3 different ways to get from A to B. And I already know that the voltage drop between A and B is going to be 0 because the capacitor is empty. That tells me something about this branch over here. There's going to be a current leaving the battery. We'll call that I1. There'll be a second current that's going to approach the capacitor. We'll call that I2. And there'll be a final current in the third branch called I3. As a result of Vc being equal to 0 at the beginning, I know that I3 must be 0. Because if there's any current flowing here, it's going to produce a voltage drop across the resistor, and that's going to break the rule that there can't be a voltage drop between A and B. If the capacitor is not producing a voltage, neither can this resistor. So I know at time 0, I3 equals 0. And that means I1 equals I2. Not only that, but I1 has to produce sufficient voltage through its voltage drop, dropping through R1, that it has to cancel the EMF of the battery. I know that because if there's 0 voltage drop here, there has to be 0 voltage drop here. That means I1R1 equals the EMF of the battery. And that's an awful lot of information to know based on really knowing nothing. That is, I can't construe anything else about this circuit. I don't know the rate at which I2, I3, and I1 are going to change, or the rate at which the capacitor is going to fill. I can't write a transient state equation and solve it. But I do know all of these things as hard facts, because the good news is, even during the transient phase of a capacitor charging or discharging, all of Kirchhoff's laws hold true. So everything we've learned about circuits is just as true during every phase of an RC circuit's charging. So even though we can't solve for the explicit values of I1, 2, and 3 at any time after 0, we absolutely know what they are at 0. Now let's shift to that point at the end after a long time. So I'll say t is equal to infinity. It doesn't really have to be infinity, but I want to make it long enough that I2 has had all the time necessary to dump all the charge on this capacitor that it wants to hold. Now imagine the scenario. The capacitor is full. That means the voltage in this branch AB won't necessarily be equal to the EMF of the battery, but it's the maximum value it's going to be. That means I2 is going to be 0 because no more current can flow into a full capacitor. That means that I1 is now equal to I3. And this node no longer breaks the current down. It flows straight through. So notice that means I have a voltage drop across here, but no current flow. So the only current flow is through the outer loop. That means I can add R1 and 2 together, and they will produce the only resistance for the remaining portion of the circuit. So I know that I1, which will equal I3, is also equal to whatever current is necessary to drive the EMF of the battery through the sum of those two resistors. So that current is going to be equal to the EMF of the battery over R1 plus R2. If I know then what I1 and I3 are, I can figure out the voltage drop across I3R2. That is, that will be the voltage drop, and that'll be exactly the same as the capacitor, because I3 going through R2 will produce the same voltage between A and B that the capacitor does. So I also know that at this point VC will be equal to I3R2. And further, that will be equal to the voltage drop in this portion of the circuit too, and that's going to be the EMF of the battery minus I1R1. So once again, even though I can't tell how it charged and what the rates of change of the currents were during the charging, I can actually solve for all of the final state conditions. This is steady state analysis. It doesn't involve solving a differential equation, but it does involve using Kirchhoff's laws to analyze the structure of a circuit, even if it contains a capacitor.